Okay. So yeah, my name is Bibi S, and I work at the ULISH Research Center. So my talk will be more focusing on the application side of using power flow models. You already heard many talks which describe the technical development of this model. So I'm involved in more in the water scientific challenge, and I will show some of the results of using this model over Europe. Okay, so yeah, so in our hydrological model simulation, so it's important to represent the subsurface properties such as the hydraulic conductivities or soil porosities, or also these hydrogeological properties such as the alluvial aquifer, like you can see in this map. To represent these type of properties in the model at a very higher spatial resolutions in order to accurately simulates these water balance components, which also includes the groundwater flow. So, but it's more challenging to implement such more complex models that can represent such type of subsurface heterogeneities, because it gets more computationally demanding. So yeah, so one such model is the power flow models, which is a more complex models and can represent the groundwater, 3D groundwater flow model. So, so in order to see the added value of using such models, so we conducted model simulations using these real world test cases. So I implemented this model over Europe and compared the results of this model, power flow model, with another model which doesn't have this type of complexities, or it cannot represent the groundwater representation. So the objective was to investigate the influence of this groundwater on other hydrological states and fluxes, such as soil moisture, ET, and water table depth over Europe. Yeah, so just talk about a little bit about these two, the differences between these two models. You already heard a lot about the power flow model setup. So this power flow is a fully 3D physics-based model, and it can simulate the 3D groundwater flow using these Richard equation and also the overland flow. While CLM can also simulate these hydrological processes, but it's a single column biogeophysical model and a land surface model, which can run serially. The code can run in serial mode or in parallel too. So it's more simple model where it doesn't have the 3D groundwater flow and doesn't represent any lateral flow in the model. So there's no communication between the grid cells. Yeah, so in power flow, vertically, we can also divide the subsurface into many layers. So in this setup, we divided the power flow up to 60-meter depth, whereas the CLM model, the soil profile was divided into 10 soil layers, which is up to 3.8 meters. So we set up these both models at a 3-kilometer resolutions over Europe. So the problem size is it's the same, almost the same for both power flow and CLM, except the layers in the vertical directions. And we ran these model for starting from 1997 to until end of 2006 for this 10 years of model simulations periods at hourly time step. So on the computational sides, so we ran the power flow on Joule's booster using the 4 GPU nodes, while CLM runs only on 4 CPU nodes. So before when we didn't have the GPU version, so we were running the power flow on CPU and it's very computationally intensive. So 1 year of simulation, we were able to finish it with around 280 hours, while with the GPU versions now it's much faster. And because CLM is more simple, use more simple schemes to simulate these hydrological processes, and it doesn't have the lateral flow, and so it runs very fast. So the 1 year of simulations can be finished in 2 hours. So in order to run these models, we also need some model inputs that goes into these models, such as the topography informations and the soil characteristics, and also the vegetation informations. And for the power flow, because it has a groundwater flow model, so it also needs additional inputs of subsurface geology. And addition to all these static informations inputs, it also needs the meteorological forcings, which is such as precipitation, temperature, and radiation inputs. So we use this Cosmo reanalysis data sets, which is available at a 6 kilometer resolutions for Europe. So here are some of the results from these two models. So I'm showing the results for soil moisture, the evapotranspirations, simulated by these two models, and the water table depth. So these are the average estimates for this time period. So the first column is for the soil moisture, which is the surface soil moisture at a 5 centimeter depth. And the second is the evapotranspiration, and the third column is the water table depth. So we can see that from comparing these two models, we see that the power flow shows more wetter soil and more enhanced ET compared to the CLM model. So I wanted to also say that both models use the same model inputs and same forcing. So these differences only comes from the model structure or the complexities between these two models. So we can see there is a very big difference in terms of soil moistures, and also we see more enhanced ET with the power flow than the CLM, and also with the water table depth. We can see that the power flow simulates more realistic water table distributions with the shallow groundwater in valleys and the deeper under the hilltops. So if we compare, these with observations, so I also compared these model results with observations to see which model performed better in terms of observations data. So here I'm showing some of the results from the validation of the water table depth. So I compared these results from these two models with the locations of, with the water table depth measurements over around 3,000 locations over Europe. And then I calculated these correlations between these two models with observations, and you can see these probability distribution functions of these correlations for different seasons and between these two models. I mean, I still need to explore this more by using showing these preliminary results shows that the CLMs perform better, particularly in the winter and spring season than power flow, but power flow has much better response in the or comparisons much better with observations in the summer season. And also here in the right side, I'm also looking at the comparisons of these two models for the water table depth anomalies for different regions. So we can see these differences between these two models, which CLM are showing when we look at these anomalies. So anomalies means that how this water table depth deviate from the normal conditions. This is we can see that CLM is showing more stronger, drier, and wetter anomalies than the power flow model. Yeah, I also compare with the surface soil moisture observations. I mean, there's not much station data available for soil moisture observations over Europe, but and for the time period, I have these simulations. So, but here I'm showing these comparisons of the surface soil moisture with the in situ observations for two different networks. So this green line is the power flow, and the black is the observations, the in situ station data, and the blue is the CLM model. So we can, from this comparisons, we can see that the power flow compares really well with the observations than the CLM models. And when I also compare with the satellite soil moisture, which is this European surface soil moisture data, the satellite-based observations, so which is at the very right-hand side map that you can see from the CCI data. So these are the anomalies for the 2003 years. So when we look at these anomalies, so we can see that the CLM has a much stronger response than the power flow and also the satellite data. So also over regions, we also can see that this surface soil moisture anomalies, there's much more stronger estimates from the CLM than both power flow and the CCI, particularly for the drought years like the 2003 years. So yeah. And then compare for the evapotranspirations validation. So I also compare these with the stations-based evapotranspirations data from the FluxNet sites. As you can see, these are the 65 stations data over Europe. And I mean, both models did very well in terms of comparing with the ET. But when I look at these individual stations, like the time series for these stations, so so you can see that the power flow is performing much better in simulating these peak ET, for example, in summer time. So matching these peaks much better than the CLM model. So yes, and also if we compare the two models, between the two models, like the power flow and the CLM, so we also see that the power flow is estimating higher ET than the CLM model, which is like 25% higher than CLM for this time period. The regional comparisons also shows that these ET increases mostly happens in the summer than the winter time period. Yes, so for the river flow, I compare these model results also with the observations from the gate stations at around for 75 river systems over Europe. So as you can see here in these maps, so I'm showing these statistical indices to show the model performance, how the model perform. So it's the correlation and also another index which called the KGE. So if the model is more, if you see more blue color, which means the model perform much better, and the red color is that the model performance is not good when compared with observations. So I mean, the correlations for both models are higher than 0.5, so which is really good, but also with the KGE values too. However, if we look at these individual stations, so we can, as you can see on the right side, where I'm just showing some these time series comparisons for different individual stations, so which is on different river systems. Yeah, we can see that again, power flow is doing very well in matching these peak flows and in most of the stations. So where the CLM is underestimating these peak flows, but in both models actually underestimates the low flows, so which is not compare good with the observations as you can see in these other plots. Yes, so I have then as a summary. So these results, we just compared these model results to show, I mean, one objective was to show the importance of having these groundwater flow models components in the power flow, and how that could influence the other hydrological variables like soil moistures and ET and the water table depth, and also wanted to show the added value of this power flow model using over larger scale and a higher resolution. So I mean, we run these model at a 3-kilometer resolutions, which is still probably coarse. We need to see the real benefit of the power flow model. We need to run these models at a much higher resolutions. But both models shows this capture this interannual variability very well when compared with observations. And yeah, but power flow, because of the groundwater, from the groundwater inputs, so the power flow shows more wetter soils and enhanced ET than the CLM models, and it's also simulates more realistic water table distributions. And because power flow doesn't have this lateral, it doesn't have the groundwater model, and also doesn't have the lateral flow, so so it cannot simulate very well these local drainages. Yeah, so in the future, we would like to extend these simulations for a longer time period, such as like 30 years, or maybe for much more longer if you wanted to do the climate impacts projections, like 100-year simulations would be needed. And also we want to perform these at a much larger scale and higher resolutions, such as at a global simulations at a sub-kilometer spatial resolution. So yeah, so this is that's it from my side, and thanks. Is there any questions? So please let me know.
Thank you very much, Bibi.